In this recording we've got two case studies related to production costs, and in particular we're emphasising that the marginal cost curve is actually a supply curve. So in this first diagram we've got a case study related to time of use pricing in the Southwest integrated system, which is the electricity system for Perth and the surrounding areas. So what I've got is the marginal cost curve. The first thing we need to appreciate is that this marginal cost curve doesn't relate to just one electricity supplier. This is the marginal cost curve for the entire SWIS or Swiss network. So this marginal cost curve is made up of all of the generators, electricity generators that are available to pump electricity into the system. So I've got on the left hand corner, bottom left hand corner here, I've got G1, G2, G3, and these are three generators. So the horizontal width of the column represents the capacity, the production capacity of that particular generator, and the height of the columns represent the marginal cost, or the cost of that generator supplying electricity into the system. So if we actually line up all of the generators from lowest cost to highest cost, and just imagine fitting a line through the midpoints of each of these columns approximately, then we get the marginal cost curve this way. So right at the bottom of the marginal cost curve we've got typically very large and cheap to operate coal-fired generators, and then as we move through we've got some wind in there, we've got some solar electricity, and then we've got coal as well. Sorry, we've got gas as well, natural gas. So the marginal cost curve is made up of different generators. Now, with the tariff system, or the price system that most people operate under in Perth, it can be best regarded as a flat tariff. So I've got a dotted line here indicating a flat tariff. So I know certainly I'm on a flat tariff system, so it doesn't matter when I actually consume my electricity, the price is the same. Now, increasingly around the world, and also to a lesser extent in Perth, this is something that was quite new to Perth, time of use pricing has been introduced. So what that means is that you need a smart meter. You get your smart meter installed, and then you can be in a situation where the electricity that you actually use is consumed or charged at different prices depending upon when you actually consume it. So what I've got here is a demand curve, a peak demand curve and an off-peak demand curve. Now, someone who's not subject to time of use pricing just pays this flat tariff, but someone who's subject to time of use pricing, someone who's actually got the smart meter installed and wants the opportunity to consume more of their electricity at cheaper off-peak prices, they would actually be subject to a price TOU1 during peak times and a price TOU2 at off-peak times. Now, in many places there are more than just these two prices, but I'm just using a two-price example to keep it nice and simple, to try to get across the concept, the key concept of this. Okay, now one problem with a flat tariff is the following. If everyone is charged a flat tariff, and I should mention these demand curves are the total demand for electricity across the Swiss network. So this is every individual household and business aggregate up their demand at different prices, and we have these demand curves here. So it's total system-wide electricity. Now, if everyone is subject to a flat tariff, then during peak times at that price flat tariff, the demand is going to be A. Now, then, of course, if the level of demand is A, then the marginal production cost of the last unit will be B. So all of the units from G1 right up to point B, all of those will need to be producing electricity under a flat tariff at peak times. In off-peak times, demand will be E, so we'll only need generators up to point E actually operating. Okay, so one issue associated with or one benefit associated with time of use pricing is the following. If everyone in Western Australia went to time of use pricing, then they would be subject to TOU1 during peak periods. Now that slightly higher price of TOU1 would actually reduce the level or reduce quantity demanded from A back to point C, and presumably we would have some people just cutting back their electricity, just being a little bit more careful, not leaving lights on, etc., etc. And also we would have people switching their consumption from peak to off-peak times. So, for example, you would run the washing machine or the dryer or whatever electrical appliance you could actually switch your use of from peak to off-peak. So you'd start doing your washing at night, etc., etc., rather than during the peak times during the day. So we would have a little bit of a consumption reduction as we move from A to C, and a little bit of load shifting from peak to off-peak times. Now, one key benefit of having this higher price during peak times is that the overall level of demand drops from A to point C, and then therefore one benefit associated with that is less capacity is needed, less generating capacity is needed to cover those very high levels of demand during peak times. So looking at this, if we can successfully reduce demand from A to C, the question is how many generators could we then not use during peak times. So perhaps we could get away with having one or two fewer generators if we could actually reduce demand during peak times. So that's one advantage of time of use pricing, just trying to reduce overall demand at peak times. And also the side benefit of that, or major benefit of that, is having fewer or less electricity production capacity. Okay, of course there is another issue associated with moving from the flat tariff to TOU pricing, and that has got to do with the deadweight losses that are involved. And these areas A, B, C and E, F, G are both deadweight loss triangles. And the explanation goes like this. Under a flat tariff, and really this explanation is hinting at the fact that time of use pricing, because we can actually move to an equilibrium price under time of use pricing in both peak and off-peak times, we're going to get a more efficient solution. With the flat tariff, at peak times we've simply got excess demand, and at off-peak times we've got excess supply. Now with the flat tariff at peak times, the issue there is initially it looks like we've got excess supply between A and where the flat tariff crosses the marginal cost curve, so we've got excess demand. But with an electricity system like this, you can't have excess demand, so the regulators, you can't have excess demand because there would be rolling blackouts. So the regulator has got to step in at this flat tariff and basically force generators to supply at point B, and then you get into some very high marginal cost electricity supply. So let's get back to this idea of a deadweight loss. The area EFG is a deadweight loss. Okay, why? Well, under the flat tariff, the level of demand is E. If we went to a time of use off-peak price of TOU2, the level of demand and also supply in the system would be equal to G. Okay, so if the price is actually at E, the problem with that is that if we could somehow move to point G, if we're under a flat tariff and we're at E, but we could somehow move to G, then we would increase both consumer and producer surplus, because the problem is for all of those units of electricity between, say, F and G that are not produced when a flat tariff is set during an off-peak time, for all of those units F to G, the marginal cost of producing those units is well below the marginal benefit of those units, which is given between E, the points along the demand curve between E and G. So the problem of not being at equilibrium, the problem of being at point E under a flat tariff and not at equilibrium, is that all of those units between F and G are not produced when we're at point E. And the problem with those units between F and G not being produced is that the cost of producing those units is well below the marginal benefit of those units. So by simply moving the price from the flat tariff level down to TOU2 during off-peak times, we can actually move to the true market equilibrium, and we can actually increase both consumer and producer surplus by a combined amount of EFG. So hopefully that makes sense. With the area ABC, that's also a deadweight loss. The problem there being, if the flat tariff is set, demand is A. Now the electricity regulator will not want a level of demand equal to A at the flat tariff and not have enough supply to satisfy the demand. That doesn't make sense for a commodity like electricity. So supply will be pushed up to B. Now we could actually get rid of this problem by simply pricing the market at the equilibrium price during peak times and have the market operate at point C. Now the problem with not having the market operating at C and having the market actually operate at and supply electricity at point B is that for all of the units of electricity produced between C and B, the marginal cost of production of those units far exceeds the marginal benefit of those units, or, in other words, the willingness to pay of consumers for those units. So we've got all of the points along the marginal cost curve between C and B representing the cost of producing those extra units of electricity beyond the true equilibrium value. But the marginal benefit of those units only equals the points along the demand curve between C and A. So it seems crazy that we're actually pushing demand out to point A and producing units of electricity which cost a lot more than the true marginal benefit of those units of electricity. So really that's the answer to this case study. We can improve the efficiency of the market by allowing the market to move to equilibrium at C during peak times and at G during off-peak times. One of the problems with this, of course, is getting everyone hooked up with a smart meter to the system. That's quite costly, but once that actually occurs, the market can generate a better produce a better outcome. So also, apart from that, the fact that we can eliminate deadweight losses by using these time of use prices, just keep in mind that if we can also use time of use prices to cut back demand during peak times, then we may need one or two fewer electricity generating plants over the longer term. So that's the first case study. The second case study relates to the iron ore market, and what I've got here is a iron ore supply curve. So this is very similar to the electricity example. Each of these coloured columns down here represents a company, or in some cases a country, and the height of those columns represent the per tonne production costs of iron ore. And so once again we've got this supply curve, or this marginal cost curve, which is just created by ranking all of the different producers from lowest to highest, and we get this global iron ore cost curve. I've just imposed a demand curve here, and I've just put that demand curve in a fairly arbitrary place just to get the principle across. Now this market, let's ignore the fact that a lot of iron ore is traded subject to contract, and let's just imagine that this is a competitive market with a lot of demand, a lot of people demanding iron ore, that is the big steel plants, and a lot of different companies and countries supplying iron ore. So let's just talk about a competitive market. So we've got the supply curve in 2010. It's the pink supply curve that lies on top of these columns, and then we've got a demand curve which is downward sloping. Now, in a competitive market, the price is going to settle itself at the intersection of the demand and supply curve. And looking at this, it's around about $108 a tonne. Now, the key thing to note about that price of $108 is that that is the price that the market needs to reach to encourage suppliers to supply the level of demand that is being demanded in the marketplace. So you actually need price to rise to cover the rising production costs of these marginal high-cost producers. If the price wasn't up here at around about $105, $108 a tonne, then we wouldn't actually be in a situation where supply was high enough to match demand. So in this example, and in reality, prices are actually rising in this market up to $108 a tonne to cover the rising production costs of the high-cost producers here, between about 1,000 and sort of 1,300 on the quantity axis. These high-cost producers, price is high to cover their production costs to allow them to actually supply, and it's these high-cost producers which actually help make demand-supply balance overall. So the question is, how does the existence of these high-cost producers benefit the majors? Well, the majors are Rio Tinto, Vale, BHP, Billiton, and some of the African producers. So these are, well, actually Vale, Rio Tinto and BHP are the majors, but they're also the low-cost producers here. Now these low-cost producers are really benefiting by the existence of these high-cost producers, because it's the high-cost producers that are really raising the market price. Just imagine if the production costs of these high-cost producers were 20 to 30% lower than they are in this diagram. If that was the case, this pink line would be sort of 20 to 30% lower as we get up into the level of output sort of beyond 1,000 on the quantity axis. So this pink line would be a lot lower, and the intersection point between the demand curve and this lower marginal cost curve would be at a much lower price, and therefore the majors down here on the left would be earning a lower price. So the fact that this supply curve for iron ore, this global supply curve, is so steep at the right hand end of the supply curve really means that we have a high market price, and that benefits the majors because they're sitting there earning $108 a tonne in this diagram, whereas their production costs are only $36, $37 a tonne. Okay, so these high cost producers really do raise the market price.